were studying constraint dynamics, and in fact we saw that it is difficult to properly formulate the canonical approach if you have constraints in the system, and in particular if you have these so-called constraints, then because you cannot invert all the momenta, it becomes problematic to define the Hamiltonian in the usual sense by just taking the standard Legendre transform. Now I worked through some examples. This is to show that basically if you have what are called the free theories, where there are no constraints, say any free field theory or the harmonic oscillator, then you can quickly formulate the canonical formulation, and there is no problem in defining the Poisson brackets and the associated equations of motion, either in the Lagrangian or in the Hamiltonian framework. If there are constraints, and we took a very simple example from point mechanics, and we could see that there were a lot of problems, and you could not actually consistently define the Poisson brackets which were compatible with the Hamiltonian and so on. So as I told you, I will give you a general discussion now. So first I gave a very specific example. Now we just give a general discussion on constraints, so that you get familiar with the terminology, and you are also able to work out problems. Okay, so this is just a general discussion. Now, this is the definition of the canonical momenta, where QA are the coordinates and A say takes values from 1, 2, 3, 4 to capital A. So A going 1, 2, and then you have the QA coordinates, and associated with each value of A you have one moment. Okay? Now if there are constraints, what does this mean? Basically means that there will be some relations where the momenta will not be expressed in terms of the velocity, right? So that particular velocity will not be invertible. You cannot express that velocity in terms of the momenta. So what does that mean? It means that there are certain relations between the coordinates and momenta. And what are these relations? They are the constraints of the system. So there are certain relations between the coordinates and the and E runs from 1 to B, and of course B will be less than or equal to A, because this is the total number of variables. So B cannot exceed A, and you cannot have more constraints than you have more relations. So this in general always be less than or equal to A. So I hope you get the meaning. These are the constraints of the system. And Dirac gave them further the name. These are actually called the primary constraints. This is a nomenclature given by Dirac. Right? And why are they called primary? Because they just follow from the definition of the canonical momenta. You need nothing else. No other input, no other calculation is required. They are the basic or the primary constraints. Nothing else is required. Now, I have further told you that the distinction between what is called the weak and strong equality, and in particular the constraints are always imposed weakly. And what does that mean? That if you compute a Poisson bracket with this phi b, you cannot set phi b equal to 0 inside the Poisson bracket. Only when you have computed all the Poisson brackets, then at the end of the analysis, you can set the constraint to be 0. That's what is meant by weak equality. Strong equality, well, you can put it 0 anywhere you like. Inside the Poisson bracket, outside the Poisson bracket, doesn't make a difference. Okay. Now, two functions, suppose f and g are weakly, you say f and g are weakly identical. So the notation is like this, that is f and g are weakly identical, and then the difference is strongly equal to the linear combination of the constraints. This should be intuitively clear. If you do not understand this, think on it, why this relation happens. This happens because I have just told you the meaning of the weak equivalence. So therefore, you see, if you take the bracket of this, you take the bracket, say, of this with some constraint, you take the bracket of this with some constraint, মিতালি, না এখন আমি ক্লাস নিচ্ছি, না তুমি 5টা সাড়ে 5টা নাগাদ এসো। আর 5টা 25 নাগাদ এসো। থাকো 404। This, have you understood this or not? This you should understand, because this you see is weakly equal. If you take g on this side, then what does it mean? This is equal to g plus this. Then what does it mean? It only means that the difference has to be equal to just this, because otherwise you don't get the weak equivalence. Try to think, what is the weak equivalence? This, unless you understand this, it's a bit difficult to conceptually visualize the whole thing. If this is strongly equal to this, then f minus g is what? 0. Okay? If this is weakly equal to this, it only means that it can be strongly equal to a constraint, because as I have told you, if this is just weakly 0, the square of this is always strongly 0. Yes. The square of a constraint is always strongly 0, because if you take the algebra with anything, then you see one of the phi goes out, it's like this, okay, something like this. But you can now forget this part because this is sitting outside, this goes to 0. Okay. So the difference is just modulo of the constraint. Look. If the algebra of the constraints vanishes weakly, what does it mean? See, this is weakly 0. The right hand side is 0. So you should be able to express it well. No, it's a combination of the constraints. Get that point. This is the reason that you can express this difference as a combination of the constraint. Is it clear or not? I say that the Poisson bracket of two constraints is weakly 0. Then, what does that mean? I can now put this strongly equal to what? Equal to some structure F. You get this point or not? You got this? Because you see, this thing is itself what? Weakly 0. This is weakly 0. Because this is weakly 0, automatically this holds. Therefore, this is strongly equal to this. If the algebra satisfies a property like this, what do we call? We call this that the algebra is closed. This is like the algebra. The algebra is closed. This repeats itself on the right hand side. If the constraint satisfies an algebra like this, or its algebra is closed, we call this to be a first class constraint. FCC. Have you followed this? Huh? You are not there. So, what happened in last class?
Where?
What is your name?
Uncle.
You are working?
Professor
Parsamula.
Partha Gua.
Hello. Class নিচ্ছে এখন আমি। Okay. So Mr. Ankan, have you followed this?
Yes.
I told you first class.
First class.
First. If the algebra does not satisfy this Bose property, it's called second class constraint. It's called a second class constraint. Likewise, this, by the way, nomenclature, everything is of course due to Dirac, is there in his book. Not the standard book on quantum mechanics, but here's another small book. It's called Lectures on Quantum Mechanics, Yeshiva University Lecture Series, which he gave there. So likewise, you will call f, any function f will be called the first class function, provided is weakly zero, or then strongly like this. That's all. So any function f will be called a first class function if its algebra with the constraints closes. So it's weakly zero and strongly like this. Otherwise, this function will also be called a second class function. Now we come to a very important property of first class functions, namely Poisson bracket of two first class functions is also first class. Poisson bracket of two first class functions is also first class, and the proof is very simple. So let me take a function f this is what I just wrote. And another function, so g so f and g are two first class functions. Then you take the Poisson bracket of f with g, and then to check if it is first class or not, you have to take the bracket with the constraint I. That's what you have to do. Okay. Now you use the Jacobi identity of this double Poisson bracket to rewrite it as follows. You know this. This is the Jacobi identity. You know it. Note that. You know it. Okay. Then what? Then you will substitute for g phi a this relation. And then you will also substitute it for that relation. Okay. And then there's a little trick. You have the Poisson bracket of the product of two objects. So when you take, you will have a Poisson bracket of g with f. That is immaterial because outside there is a constraint sitting. So that you can put equal to 0, so that doesn't count. Therefore you are interested only in the algebra of this with this, because this is inside the group. Then this goes out. And you have phi a prime with f. That you can just write it from there. You will have another minus, that gives you plus, and a prime, a double prime, plus a prime. The same logic applies to this case also, and you will have a minus. And then you can take the phi a prime outside, and you can take a bracket. So this is the new structure. And therefore this is also first class, because you have managed to express the algebra as something times a constraint. Therefore, this is a very important result. Once again, proved by Dirac, is there you need a lot of analysis in this topic. And this is a very useful result. The Poisson bracket of the first class function is also first class. Now, so you already know the difference now between what a first class object is and a second class object is. So let us proceed. So don't follow, ask. So from the definition, so you start with a given Lagrangian, you compute the canonical momenta corresponding to all the coordinates in the Lagrangian, and then if you see that there are no constraints, then everything is fine. You don't need all this analysis. As for instance in the harmonic oscillator, and you can quickly go to the canonical formulation, give you the Hamiltonian, the one particle state, and so on. On the other hand, if you find that there are constraints, as I have just shown, then it is actually problematic to define the canonical Hamiltonian itself. So the first thing is that you have to appropriately define what? The Hamiltonian. And this was once again done by Dirac. So what he did was like this. It defines what's called now a total Hamiltonian, which is denoted by HT. This is the original canonical Hamiltonian, which you were unable to define, but which you will now be able to define in this way. I will now explain that if the HT exists, then there is a method of getting the HC, but by itself there is no HC. Just to come to that. Plus, primary constraints. Yeah? So, you find the primary constraints of the system and you introduce them through the Lagrange multiplier. Okay. And you write this to be the total Hamiltonian, where this is what you earlier could not define, but now you can. The reason is because earlier you were not being able to invert the velocities and so on and so forth. But all that ambiguity which you could not, which forced you to define this, all this ambiguity is actually thrown here into this term. It's thrown into this term. How it works, well, let me just then give you the very simple example of what's called the Maxwell theorem. I mean, all of you should know the Maxwell theorem. You know the Maxwell theorem. You don't know. You studied the Maxwell theorem. You have not studied. Your face tells that you have not studied. You studied Maxwell theorem. The simplest of all theories, but the most remarkable. Now you see, the momentum conjugate to A0 doesn't occur because there is no A0 dot Okay, there is no A0 dot term here. So this is actually 0. This is actually 0. Now, if you try to write the Legendre transform, how will you write? You will write pi 0 A0 dot plus pi I AI dot, right? Minus your L. Okay. And then you really do not know how to proceed, because if you set this equal to 0 by hand, then your A0 dot term just goes out. The pi 0 A0 dot term just goes out. Okay. But the question is, one could also say that I could write some things in the Hamiltonian as 100 multiplied by pi 0, because this is 0. So I will retain it. I will retain it. And that, of course, gave Dirac this insight. He interprets this as what? As a constraint, because there is no corresponding velocity. This is a primary constraint. Okay? So this will occur there. So you see, the so-called canonical Hamiltonian plus this will be what? Plus u0 pi 0. This term is u0 pi 0. Then you are through, because this is completely undetermined. There is a freedom. This is completely undetermined. You don't know what this is. Then there is no problem. Whether you set this equal to 0 or not, I don't care. You could as well write it just as pi 0 A0 dot, because the pi 0 A0 dot term you can even throw it in here. The u0 contains within it the A0 dot term, because it's multiplied by pi 0. Therefore, you can, when you define the total Hamiltonian, there is no problem. But this is possible only when you have this tree. Okay, so you see that this is therefore written in quotes, because really for a constraint system, the canonical Hamiltonian really doesn't make any sense at all. Right. So it is this particular Hamiltonian with which we are interested, and in computing this HC, you are now free to set the pi 0 A0 dot term equal to 0, because this freedom is already here. Here you can set the pi 0 equal to 0. There is no problem now, because it is here. It's shifted there. So this has an explicit form. Nothing is undetermined in this factor. Whatever is undetermined is in this factor. This will naturally modify the Hamilton's equations of motion. The Hamilton's equations are written as keeping a dot are now expressed in terms of what is this? This is Hamilton's equation. So now you have to write this as just to change the indices of the terms. Is it clear? Or it's not clear? It's clear. Once again you will see that when you take the derivative, I have not taken a derivative on the lambda because the phi a just sits outside. So that is dropped. The equation of motion is basically taking the Poisson bracket with the Hamiltonian. Therefore, you are free to drop this term. This means that the Poisson bracket has been taken and gives you this answer. So therefore, you see the whole point is here. This is non-zero. This is non-zero. The derivative can use something. But if you do this, the derivative is unknown because this is a multiplier. But the point is multiplied by something which is zero, and therefore Dirac is safe. It does need to compute this object. Whatever is necessary in the equation of motion can be computed modulo this freedom. Likewise, you can compute what? You can compute your PA dot, and this will be minus and these two equations will have to be supplemented by this is the whole set of equations. The whole set of Hamilton's equations is this. Okay, these three equations comprise the complete set of Hamilton's equations of motion in the presence of constraints.
So why have you replaced lambda by u? Why did you change?
Oh no, this is, you can put lambda.
We can put lambda also.
So now we go, so we have defined the primary constraints, we have classified them into first and second class, we have defined a new Hamiltonian which is called the total Hamiltonian, which is AC, plus all the primary constraints irrespective of whether these are first class or second class, all the primary constraints have to be introduced here. And this is my set of equations of motion. Now comes the requirement. This is the famous consistency requirement. So what is the consistency requirement? It means that if you have a constraint, that should be preserved in time. Otherwise, it has no meaning. I mean, the system to begin with is a certain constraint, then that should be preserved in time. But that means as it evolves, that constraint should be there. It's not that it changes to something else. So, what does it mean? It means that the time conservation should vanish. How do you compute the time conservation? Is you have to take the bracket with the Hamiltonian. And what is the Hamiltonian here? Is the total Hamiltonian. So, this will give us three possibilities. When you compute the consistency requirement, that is phi a with ht must be weakly 0. Right? All that we need is that the constraint should be time conserved, at least on the constraint shell, on the constraint surface.
So you have put Vt is equal. So you have put Vt is equal. Why not strongly is equal?
No. All you see, as I have just told you, all these equations, although they are written like this, when you take the bracket with the total Hamiltonian, they are all weak brackets, because eventually you are dropping this term. You follow? If you take the strong bracket, then what does it mean? You can't take the strong bracket, then this term would not contribute at all. The constraints are always imposed weakly, and this equation, as it is written here, is actually taking the weak bracket with the total Hamiltonian. If you take the strong bracket, it means that this term will never contribute. It will just drop. Therefore, effectively, when I have written all this, it's basically the weak bracket, always the weak one, the weak bracket. Right. So there can be three possibilities. The one is the trivial possibility, 0 weakly 0. That is, you compute the left hand side and you get 0. That's trivial. That is 0. Of course, it's obviously weakly 0. What to do? 0 nothing to do. Then 2 fixes the multiple. Now how does it fix the multiply? Next. So from the left hand side we get this, and once again you see that the algebra of phi with lambda doesn't matter because phi a prime goes out, that term is 0, it drops out. Right. Now of course you see that if this bracket which I have written is weakly 0 by itself, then this is gone. Then lambda cannot be fixed.
First one is
So
the
if it is first class constraint,
Right. If this is a first class constraint, then lambda will not be fixed. Okay? And that is why we call the first class theory to be a gauge theory. The freedom cannot be fixed. That is a gauge theory. This shows up from Dirac's analysis. Okay? So if you have the first class constraint, in the Maxwell theory the pi 0 is a first class constraint, you cannot therefore fix the multiplier. There is a freedom in the equations of motion therefore, and that's a gauge theory. It comes out very nicely, you cannot fix it. On the other hand, if the constraint is second class, then this is not weakly 0. This is something. And then of course, it basically means that this is invertible. And then of course you can compute your lambda a prime. So for a second class system, the multiplier is fixed by this equation. So second class constraints. So this is the other possibility. That if you have second class constraints, you will be able to determine your lambda and consequently your complete total Hamiltonian is determined. Then the last possibility, third, well this is the possibility that is new constraints. These new constraints. So when that possibility can occur is suppose this is first class, so this term goes out. and this term gives me something. It will be some function of the coordinates and the momenta, and that has to be equal to 0. But the relation between coordinates and momenta, which is equal to 0, with equal to 0, is a constraint. So this is a new constraint of the system, and this is being generated by the primary constraint, by the time conservation of the primary constraint, and it is called a secondary constraint.
So please repeat.
So there could be an instance when this is weakly 0, so this goes out, and this is not weakly 0. This is some finite thing, which is a function of the coordinates and momenta. The right hand side is to be weakly 0. Then what is that? That is a relation which tells that there is some condition between the coordinates and momenta, and this is a new condition which comes out from the consistency or the compatibility from the preservation of the first class constraint, the time preservation of the first class primary constraint. And this is called a secondary constraint. So now you learn that the primary constraint, it could be both first and second class. If it is a second class, then that will fix the multiplier. Okay? If it is a first class constraint, then there could be two possibilities. One possibility would be that, well, the whole left hand side is trivially 0, gone. But there could be another possibility that the whole left hand side is not trivially 0. It's some functions of the q's and the p's, which does not involve the lambda. And that is a new constraint, and that's called the secondary constraint. And this process has to be iterated. When you get the secondary constraint, you have to again take its time conservation. Otherwise, there is no meaning. It also has to be time preserved. So once again, you have to take its algebra with HT. Once again, there will be three possibilities. You go on, and this iterative process will stop when you come to this point, because then it ends. And you get your complete structure of the constraints, all the constraints with you. So you have now understood the meaning of what's called the primary and the secondary, of all the constraints which is generated from the secondary, sometimes called the tertiary, but then most people avoid this. Anything, there is two classes, you have primary, and subsequently all set of constraints are called secondary. Finished. And you have another distinction which is called the first class and the second class. Even amongst these, even among the secondary, you can again have this distinction in the first class and second class, and so on and so forth. But when you have determined your full constraint structure, then you have to perform the algebra. You have to take the algebra of the whole set of constraints and then see which are first class and which are second class. So suppose you have phi 1, phi 2, phi 3, phi 4. You find that the algebra of phi 1 closes with all. Then that is what? That's a first class. Algebra of phi 2 doesn't close with all. It closes, say, with phi 1 and phi 3, but doesn't close with phi 4. That's a second class. By the same logic, phi 4 would also be second class because it doesn't close with phi 2, and so on. So you have to, this is called the famous classification of the constraint. That's not an easy task always. In simple models is okay, but particularly in gravitational models it's very difficult to classify the whole set of constraints. Okay. So I think I will stop at this point, right? So I have given you the Hamiltonian, the classification of the constraints. So this is a completely general discussion, nothing to do with any models or anything. Although it's written in quantum mechanics form, but nothing prevents you from doing field theory or anything. Only thing is you have to be a bit more careful with the indices. That's why you have to appropriately the space-time index will come. But that's only a technical point. There's no new concept. Are you following this or not? Huh? You're following this. But you are not there.
I was thinking.
You see, the point is you should work it out. You should do work it out on your own. Sometimes you might feel that you are understanding the thing, but it may so happen that you have not understood it. So it's better to actually practice it. I'll proceed in the third class also with certain general discussion, and in the fourth one I'll walk through a very specific example, the Maxwell theory.
So there's one question I have, only one. So when you take the strong equality, why do you consider that the subsequent thing on the right hand side is only linear in phi's? It obviously doesn't matter classically. You can have phi squared, phi cubed, phi 4.
No, I told you that the definition of the constraint surface. Huh?
Right.
So if phi equals 0 is my constraint surface, then it will not be the phi square equal to 0 is a
It's
constraint.
meaningless in that sense. But when
It's
you
not-
go to a quantum
it's-
theory
it's-
code,
No, not even in quantum theory, because you have to first here define the classical theory, and in quantum theory phi square actually has no meaning,
okay. So it's
because
just
there are
I see.
ordering problems, there are ordering ambiguities and so on, and you have to appropriately look at it. Phi square really has no
But it's
meaning.
not summed over the same phi, right? I mean, it can be phi 1, phi 2.
Yeah, but you cannot write phi 1, phi 2, you can have n number of orderings. I can write phi 1, phi 2, I can write phi 2, phi 1, I can write phi 1, phi 2 plus phi 2, phi 1, phi 2 or whatever I like. So there is no meaning to the product. Yeah? So you just keep it linear. And that actually gives you an essential handle on how you can interpret the phi as the generator of the gauge transformation. Effectively, you can subsequently see that this phi is really the generator of the gauge transformation.